Okay, let's unpack this. We're diving into the machine tool world today.
Yeah.
Specifically tackling one of the most critical and, frankly, most expensive decisions any shop faces when they're looking to level up.
Choosing the right 5-axis.
Exactly. Picking the correct architecture for a 5-axis machining center. I mean, this machine, it's going to basically define the limits of your work for, what, the next decade?
Easily. Yeah, the complexity, the size, the weight, and crucially, the materials you can actually cut profitably.
It's a huge commitment. It's not just buying a machine.
No, it's a commitment to a specific type of geometry you can produce. And the dilemma we see constantly tripping people up, even experienced engineers, is that choice between the two main styles. The Trunnion-Style, where the table itself rots.
Rocking table, yeah.
Or the Swivel-Head machine, where the actual spindle assembly articulates.
So our mission today is really to boil down those practical differences so that you, listening, know precisely which configuration your parts, your specific parts, really demand.
Because that's the key.
Because here's the main takeaway right up front. If you're staring at a machine catalog first, you've kind of already missed the point.
You're starting in the wrong place. The secret is stop looking at the machine. Start by really analyzing the parts you need to make. Or the parts you want to make.
The part tells the story.
Always. It always tells the story. And the costs of getting this wrong are, well, they're huge. I've seen shops buy these beautiful, fast Trunnion machines, only to realize the tilt mechanism just can't handle the sheer weight of their most profitable jobs, maybe a big defense contract part or something.
Ouch.
And conversely, I've watched other shops struggle for months trying to machine, say, intricate fuel nozzles on a big swivel head because they just couldn't get a short, rigid tool into those deep undercuts without, risking a spindle collision. It's terrifying.
That structural mismatch?
Yeah.
That's the killer. So before we go deeper, let's just clarify the axis, the movement.
Good idea.
We talk 5-axis. We're adding 2 rotational axes to the standard 3 linear ones. Typically, that's the A-axis, which is the tilt or the rocking motion. And the C-axis, the full 360-degree rotation.
Correct. And in a Trunnion machine, both A and C, those rotations, they happen in the table. The table tilts and spins. In a swivel head, both A and C are up in the spindle. The head tilts and rotates.
Got it. So where those axes live defines, well, pretty much everything else.
It dictates the entire machine's capability, fundamentally.
Okay, so let's start with the swivel head configuration then. If your shop is doing, say, massive die castings, huge aerospace frames, big energy sector parts.
Yeah, things measured in meters, not millimeters.
Right, and weighing hundreds, maybe thousands of kilos. This machine sounds like it's your go-to.
It's your champion, exactly.
So why? Why is the swivel head better for handling all that heft?
It really comes down to pure physics. The swivel head design completely isolates the part weight from those sensitive rotary axes we just talked about.
Isolates it how?
Well, the heavy workpiece. It gets clamped onto this large, usually stationary table. That table only moves linearly in X and Y. Think of it as just this incredibly strong foundation.
So the table itself isn't doing the tilting or rotating, it's just supporting the load.
Exactly. It's bolted down, structurally speaking. It never has to fight gravity to tilt, a 2-ton block of steel. All the complex A and C rotation, the dynamic stuff, it happens way up in the spindle head assembly. And while that head is complex, it's significantly lighter than the massive workpiece it's machining.
Okay. So the design is just inherently built for load-bearing stability.
That's its core strength.
And the separation of the load, that directly leads to its main advantages, right?
Absolutely. So benefit number 1 is obvious. Weight capacity. A really high-performance Trunnion machine, maybe it hits a ceiling around, say, 500 to 800 kilograms of dynamic load. Maybe a ton tops on some specialized ones.
Okay, still a lot, but...
But a comparable swivel head machine's table. It can easily support several metric tons, sometimes 10 tons or even more, and that weight has almost negligible impact on the machine's stability during cutting.
Wow, that's a huge difference. What about the work envelope? I know Z-axis clearance can sometimes become a real headache.
That's benefit number 2, and yeah, it's critical for large parts. Think about what happens on a trunnion when you tilt a big blocky part.
The top corners swing up and out.
Exactly. They swing towards the machine column, and that rapidly eats up your available Z-axis travel. You can lose a huge chunk of your usable work envelope just by tilting the part 30 or 40 degrees.
Okay, I see.
The swivel head completely avoids this. Because the part stays flat on the table, the work envelope stays pretty much consistent regardless of the tool's orientation. And that's crucial if you're machining things over, say, 2,000 millimeters, those massive parts you see in turbines or big molds.
So if I'm hearing you right, the swivel head is fundamentally trading maybe a bit of tool dexterity for the sheer unbeatable ability to carry massive loads and maintain a large, consistent working area.
That's the essential trade-off, yes. Heavy and big.
Okay. Now let's flip it. Let's talk about the Trunnion architecture.
Yeah.
If the swivel head is the heavy lifter,
yeah,
the Trunnion seems like it's built more for agility, for intricacy, the kind of machine you'd want for high-value, complex things like small medical implants, maybe aerospace blisks, small molds with deep pockets.
Exactly. The Trunnion is all about access. Think about doing micro-machining or complex five-sided work on a small part.
Right.
You wouldn't try to bend the whole machine head down to look at the underside, right? You just tilt the object in your hand to bring the feature you need to see closer.
Okay, that makes sense.
The Trunnion machine does exactly that. It has the ANC rotary axis built into the table. So the table cradles the part and tilts it, often through a huge range, maybe -30 to plus 110 degrees even.
It moves the part out of its own way, essentially.
Yeah, precisely. It moves the part relative to a stationary tool path, in effect.
And this tilting action, that must be absolutely key for things like undercutting.
It's the defining feature. That's why people buy them. The Trunnion provides far superior tool access compared to a swivel head for complex geometries.
How so?
By tilting the part itself, you create this huge clearance area around the tool. It makes it much easier to reach deep undercuts, complex side features, thing that would force you to use dangerously long tool stickouts on a swivel head.
Okay, and this leads us straight to what you hinted at as the Trunnion's maybe most important advantage, but one that's often misunderstood.
Yes. Tool rigidity and performance. This is where the game really changes for certain types of work.
Rigidity, explain that.
Because the Trunnion tilts the part into the tool's optimal cutting position, it allows you, in fact, it enables you to use the absolute shortest, most rigid tool possible for the job.
And short tools are better because?
Because shorter tools mean dramatically less deflection, less vibration, physics again.
Right, less leverage for bending forces.
Exactly, which means you can push your feeds and speeds much, much harder. And that translates directly into better surface finishes, holding tighter tolerances, and of course, shorter cycle times, more parts per hour.
Can you maybe elaborate just a bit more on the engineering side of that tool length issue?
Yeah.
Because that feels like a really key technical point for our listeners.
Absolutely. This is the rule engineers live by. Tool deflection isn't linear. It doesn't just get a bit worse as the tool gets longer.
Right.
Deflection actually increases exponentially. Specifically, it increases by the cube of the tool's stick-out length, the unsupported length from the holder.
The cube. So if I double the tool length.
If you double the stick-out length, you increase its tendency to deflect by 8 times. 2 cubed is 8.
8 times the flex just from doubling the length needed to clear something.
Yeah.
That's a massive penalty.
It's a huge performance killer, and that's the swivel head challenge for certain parts. To reach a deep side feature, the head itself has to tilt way over, and that often forces you to use a much longer tool holder plus a longer tool just to keep the expensive spindle nose from crashing into the workpiece or the fixture.
Makes sense.
And all that extra length. It introduces flex, it introduces vibration, and it forces you to back off your cutting parameters dramatically, especially if you're cutting tough materials like titanium or Inconel.
Okay, right. So let's take that insight and apply it directly to the rigidity showdown. If we are trying to really hog material, deep, heavy cuts in hardened steel or aerospace alloys, which structure actually gives you more stability right where it counts at the tooltip?
Okay, so here's the conclusion that often surprises people. A Trunnion-style machine generally offers greater effective rigidity right at the cutting edge.
Wait a minute. You just spent time telling us the swivel head has that massive stationary table, the rock-solid base.
I did.
So why would the Trunnion, which is dynamically tilting a potentially heavy load, win the rigidity contest? That seems counterintuitive.
It does, but remember, rigidity is about the entire system, machine, fixture, tool, workpiece. And the cutting performance is always limited by the weakest link in that chain.
And the weakest link is usually?
It's almost always the tool itself, especially the stick-out length. The Trunnion's design lets you dramatically shorten that weakest link.
Ah, I see. So the rigidity advantage isn't necessarily in the base casting itself.
Not solely, no.
But in the geometry the machine enables you to use at the tooltip.
Precisely. The swivel head might have a theoretically stiffer base structure overall, sure, but the articulation required way up in that spindle head often forces you to use that longer, less rigid tool setup to achieve clearance.
Which effectively negates the base advantage when you're doing aggressive cutting.
Exactly. That long tool becomes the limiting factor. And structurally, don't underestimate the trunnion mechanism itself. While it moves, it's often a very, very robustly engineered component, highly damped, designed to handle massive clamping forces and dynamic loads. Whereas the swivel head's articulating spindle assembly, just by its nature, has more moving joints, more bearings, more mechanical connections up high.
Potential sources of vibration.
Potential sources of vibration or loss of stiffness, especially when you're applying really high cutting forces sideways onto that extended tool.
Okay, that clarifies a lot. So we could sort of summarize the material match based on this rigidity insight. If you need to remove serious amounts of tough material, deep, powerful roughing cuts,
then you strongly favor the trunnion because it lets you use that shortest, tightest possible tool engagement, maximum metal removal rate.
Okay, and if you're doing lighter cutting?
If you're doing lighter cutting forces, maybe high-speed finishing of complex 3D contours like in mold making, or maybe machining softer materials like large aluminum parts where speed is everything but the depth of cut is relatively shallow, then the swivel head often performs beautifully and might even be faster overall due to potentially higher rapid traverse rates on the linear axis.
This is a really huge distinction. And it leads us right to the bottom line, the actual investment decision. I mean, hundreds of thousands, maybe millions of dollars are on the line here.
It's a major capital investment.
So we need a clear checklist, something focused entirely on the part, not the glossy machine brochure.
Let's try and simplify that buying process right now.
Yeah.
You absolutely have to match the inherent strengths of the machine architecture to your actual or your desired production needs. Don't buy the machine you like. Buy the machine your parts demand.
Okay, let's run through the critical questions then. Number one, typical part weight. You need to picture the difference between, I don't know, a small titanium aerospace bracket versus a massive cast iron engine block.
Exactly. So if your parts are consistently heavy, let's use that 500 kilogram mark again as a rough guide, maybe half a ton, scaling up easily into multiple tons.
Yeah.
Then you're pretty much locked into the swivel head. The physics demand it. If your parts are generally lightweight to medium weight, under that rough threshold, then the trunnion is often the more flexible and potentially more precise choice.
Makes sense. Question 2, typical part size.
Yeah.
This isn't just about weight, it's the physical dimensions.
Right. If your parts frequently exceed, say, 1,000 millimeters, a meter long or wide, or if you're hitting those really big aerospace dimensions, 2,000 millimeters and up, then the swivel head is almost certainly necessary just to maintain that generous, consistent work envelope we talked about.
To avoid the part hitting the machine as it tilts.
Exactly. For anything smaller to medium size, generally under that meter mark, the trunnion often offers the highest, let's call it precision density, more capability packed into a smaller footprint.
Okay. Question 3, part complexity and tool access. This seems like where the trunnion really comes into its own.
This is its home turf. Ask yourself, do parts have deep, intricate pockets, internal cooling channels, critical undercuts that are hard to reach, complex blade geometries like on blisks or impellers? You absolutely need the high tilting range and the superior tool access of the trunnion design. If, on the other hand, your parts are predominantly large plates, simple structural frames, or maybe 5-sided blocks where the geometry is complex but doesn't require those extreme undercuts or deep reaches, then the swivel head is often perfectly adequate.
Got it. Question 4, materials cut and the type of cut. Back to the rigidity test.
Yeah. Are you primarily taking heavy, deep roughing cuts in difficult materials? Think in conal, hardened steels, titanium alloys.
If that's your bread and butter.
Then the trunnion's tool rigidity advantage becomes pretty much non-negotiable for maximizing productivity. If your work is mostly high-speed finishing, maybe on aluminum, composites, or other softer alloys where you're taking light cuts, then the swivel head is often faster and more efficient for that type of work.
Okay. Question 5, operational priority. Thinking about bottlenecks. What is the single most critical factor limiting your performance right now?
Good question. If your absolute top priority is getting maximum tool access for undercuts, achieving zero tool deflection for perfect finishes, and hitting the tightest tolerances possible,
Trunnion.
You need the trunnion. If your top priority is handling maximum part weight without compromise, or avoiding any shrinkage in your available work envelope for very large parts.
Got to be the swivel head.
It has to be the swivel head. Choose the machine that solves your biggest problem.
And finally, question 6, production style. What's your business model? High volume or high mix?
Right. If you run high-volume batches of smaller, highly complex parts where minimizing tool changes and maximizing machine uptime is key, think continuous production of medical implants or something similar, that really plays to the strengths of a dedicated Trunnion setup. If you're focused more on low-volume, high-mix, maybe highly custom, unique jobs on extremely large one-off components.
Like huge molds or aerospace prototypes.
Yeah, exactly. That really demands the flexibility and sheer capacity of the swivel head.
So the machine choice, then, it really isn't about preference or which one looks cooler. It's about aligning your shop's competitive advantage with the fundamental structural reality of the machine.
That's the synthesis right there. The Trunnion machine is, generally speaking, the undisputed king of precision, accessing complexity, and delivering effective tool rigidity for small to medium parts, especially in tough materials.
And the swivel head.
The swivel head is the unbeatable choice for sheer scale, for load-bearing stability, and for efficiently handling those massive components found in heavy industry, energy, and large aerospace.
Okay. So here is the final provocative thought for you, the listener, to chew on as you consider this big investment. The purchase of a 5-axis machine isn't just buying hardware. It's really an investment in your future market share and the kind of work you'll be able to win.
That's a great way to put it.
So as you review your top 10 most profitable jobs today, and maybe even more importantly, think about the top 10 jobs you wish you could successfully bid on right now. Ask yourself this critical question. Does the machine architecture you're considering today inadvertently limit your capacity for tomorrow's highest profit opportunities?
That's a sharp point.
Because if your potential new machine can handle the necessary weight, but it can't effectively machine the undercuts required by the next generation of complex components.
Or the reverse.
Or if it provides fantastic tool access for intricate parts, but it simply cannot physically lift the larger structural frames your best customer is asking you to quote.
Then you've already made a decision.
Then you are essentially predetermining who your most profitable customer can be in the future, and you might be placing an artificial cap on your shop's ultimate growth potential.
Choose wisely. It's more than just metal.
Absolutely. Food for thought.